In the last video, I've talked about how to obtain Einstein's equation for photoelectric effects by considering the conservation of energy and work function and kinetic energy. So basically, the photon energy would be converted into, would be used to do work for the work function, and whatever remains would become the kinetic energy of the electron. So this is the idea. Now in this video, I'm going to look at some example calculations that we can do using this equation. Just clear this. So let me start with the example that this is made of sodium. This cathode is made of sodium metal. Now, sodium, it's a nice example here because its work function tends to be lower, so that we can use light. We can use light that is somewhere in the middle of the visible spectrum. If I use other things like maybe zinc or copper, it would have a higher work function and would require maybe light that is in the violet or even the ultraviolet frequency, which we can't actually see. Right, let me start with the first exercise. The first exercise, I want to find what is the frequency needed to just overcome work function. Okay, so we need some numbers for this, and in the case of sodium, the work function is 2.38 eV. Right, I think that's all that we need. Now we would need to know the Planck's constant for these calculations. That would be 6.63 times 10 to the power of minus 34 joule second, and we would need the electron charge as well. Right, so that's 1.6 times 10 to the power of minus 19 Coulomb. Right, so what is the frequency needed to just overcome phi? Now we can always use Einstein's equation, but once you understand that it comes from the energy conservation, from the photon energy changing the work function and kinetic energy, we can just make it up or make up parts that we need as we go along. So let's do that here. Frequency needed to just overcome the work function. So that means that the photon energy is, we're talking about photon energy that is just enough to eject the electron, just enough to do this work. So that means that what we need is just HF equals to phi. Photon energy just equal to the work function. So we don't even need to write down Einstein's equation and use it. We can just make this up from the question, or the question. And the question is to find this F. Okay, this F here, therefore, we can solve this equation. Just make F the subject by dividing by h on both sides. So we get F equals to work function over Planck's constant. The work function is 2.38 eV. We need to change that to SI units. So, and that means in joules. So I need to take 2.38 times the E here for electron charge, 1.6 times 10 to the power of minus 19 over Planck's constant, which is this 6.663 times 10 to the power of minus 34. And the answer is 5.706 times 10 to the power of 14 Hertz. And this just so happens to be green light, the frequency of green light. And the frequency needed to just overcome phi, if you remember, it has a name. It is called the threshold frequency. Okay, so that's our first exercise on the photoelectric effect. So if I use this exact frequency for my light shining onto the cathode, let's think about what would be the Ke, kinetic energy of the electron ejected, and the stopping potential. And the answer is quite simple. Since at this frequency, the photon energy is only just enough to overcome the work function, that means that by the time the electron gets ejected, the electron has used up all the energy that it has absorbed from the photon, meaning that it is left with nothing, no energy. And that means that the Ke would therefore be 0 joules, no Ke. And if the Ke is 0 joules, how much reverse potential would you need to stop it? You don't need any, you just need 0 volts. So these are the answers. Now that we have looked at green light, let's push up the frequency a bit and let's try blue light. Clear this. So let me look at my next example. I'll use blue light with a frequency of let's say 650 terahertz. And the question is to find, let's start with finding the kinetic energy. Okay, so this time we have blue light coming in instead of the green light. Blue light, this little blue photons, lots of blue photons hitting the sodium metal. What's the K if these are the photon frequency? Okay, so the photon frequency has energy HF, right? And to eject the electron, it uses up some of the energy to work, and that's the amount of work that it needs to do, the work function. So it's left with the difference. The difference must be the kinetic energy. Okay, and it's good to remember that this is the maximum kinetic energy, because most electrons would have lower energy than this, because they might collide with other atoms before coming out. So this is what we need to find, the maximum kinetic energy. And if you look at these symbols, we know H from there, we know F from here, we know phi from there. So we know we have all the numbers. So let's do the calculation now. H is 6.63 times 10 to the power of minus 34. F is 650 times tera is 10 to the power of 12. So this is HF minus phi, right? That's an EV. So we need to take 2.38 and multiply it by E. 1.6 times 10 to the power of minus 19. So using our calculator, we would find 5.258 times 10 to the minus 20 joules. That's an extremely small number, and things tend to get a bit abstract when we look at numbers that are either too small or too big, sort of very far from what we are used to every day. So let me add one more item to this question. Find the KE and find the velocity. So to find the velocity, I need another number. I would need the mass of the electron. Let's see, that would be 9.1 times 10 to the power of minus 31 kilogram. So, right, what I really want is the Vmax, maximum velocity. So now that I know that the half mv squared, this is really me, mass of the electron, is equal to this answer, I can solve for it. Let me call this E. So that's E. Okay, so Vmax therefore is equal to, let's make V the subject, bring 2 over, bring m over, get 2e over m, and then square root the V squared to get V. Let me write this out more carefully. Square root of the whole thing, m a little e, for the electron mass. Using this value for E here, and that value for m here, we can use our calculator to find the answer. That would be 3.398 times 10 to the power of 5 meters per second. So again, a number that's much bigger than what we're used to. Not quite, but nearly 1,000,000 meters per second speed. And maybe finally, one last bit. Let's try and find the potential, the stopping potential that we need to stop this electron. So this will be my final example here. find the stopping potential. Right. So for this, I would need the previous results. So previously, we obtained half mv squared maximum ke. We obtained 5.258 times 10 to the power of minus 20 joules. We need to make use of this here, and the understanding is that this kinetic energy would be used to do work against the repulsion from the negative charges here when a stopping potential voltage is applied between these two plates. And the stopping potential is the voltage that is needed to just stop the electron, meaning that all of this kinetic energy would just be used up by the time the electron reaches the anode. So therefore, if Vs is the stopping potential, then this kinetic energy must be used to do work against this potential. Right, must be just equal to the work needed to go against this potential. So therefore, Vs would be equal to is half mv max squared divided by charge of the electron. Using this answer for kinetic energy and this value for electronic charge, we find 0.3282 volts, and that's the voltage we need to just stop the current if we shine blue light on a sodium anode.